Can you hear me?
Yes.
Okay. Arigato-san. Hello, everyone. My name is Chikyo Lo. You can also call me Jackie. I am a research officer at the NRC. These are the awesome people I work with in the multilingual text processing team. In this presentation, I'm going to give an overview on the large-scale natural language processing research at the NRC and discuss some potential collaboration ideas for Fugaku. So at the NRC, we have two research groups working on a wide range of NLP topics. The multilingual text processing team works on machine translation, cross-lingual and multilingual language technologies, and indigenous language revitalization. The text analytics team works on medical and biomedical language analytics, web-scaled unsupervised information extraction, emotion and sentiment analysis. And recently, we also start working on ethical and de-biasing language technologies research. Since I come from the multilingual text processing team, I will talk more about our machine translation and multilinguality work. So I know not a lot of you have natural language processing background, so let me first have a very brief background introduction on neural machine translation and we can have some basic idea of how does it work. So to train a neural machine translation system, we need very large amount of parallel training corpora. They are usually human translated sentence aligned document. The development set is also a set of unseen parallel sentence pairs for checking whether the system is training in the right way. So at testing time, the original text in the source language is inputted in the neural machine translation system, and then we will receive the translation hypothesis in the target language. To evaluate how good the system is performing, we compare the predicted translation output against the human reference translation. And we put it into an evaluation metric, and it will return scores that reflect the translation quality. So since translation, or in general, text generation does not only have one single gold standard ground truth, there are, for the same source input, we could have different possible translation. So evaluation metric itself is an independent research topic. Later, I will talk more about this part. So we look closer at the neural machine translation engine. So this is essentially a sequence-to-sequence encoder-decoder model. So input sequence of word tokens is encoded into a vector space, and then it will feed through the neural network. And then where the sentence meaning is built up in the network, and the decoder will try to predict the first token of the translation based on the information it sees through the neural network. And then what we'll do is we'll feed this predicted token back into the neural network so that it will guide the neural network to predict the next token, and then so forth, and then so forth. So this is what we call a sequence-to-sequence encoder-decoder model. So different types of network architecture could be used to build this neural network system, a neural machine translation system, such as long short-term memory, convoluted neural network, recurrent neural network. They can all be used. Currently, the state-of-the-art neural machine translation system usually use the transformer architecture. So the transformer architecture, the characteristic is that we have inserted an attention layer that will the network will learn to decide which input token or input features to weight higher at each point of the decoding time. So it's so we have a sequence of input, and then when we are predicting each token of the translation, the attention layer will tell us okay, now I should look at which word in the input sentence. So right now, this is the kind of the de facto state-of-the-art system. So now we have a basic idea on how NMT is done. So we can move on to talk about the work we did on multi-source transformer for Kazakh, Russian, English NMT. This is our submission to the 2019 Conference on Machine Translation Shared Task. It's pretty much like a competition, a research competition on translating Kazakh into English. So, so the problem we have on hand here is for building Kazakh English neural machine translation system, there is relatively little Kazakh English parallel data, only 200K sentence pairs. However, we have there are much more Kazakh Russian and Russian English parallel data, 5 million sentence pair and 14 million sentence pair respectively. So this this unbalance of data available poses some challenges. But honestly, we are not particularly interested in Kazakh English translation. This data situation is actually very similar to the situation we have on hand in working on Canadian indigenous languages. So Yupik is an indigenous language spoken in Central Alaska and St. Lawrence Island, an island in between Alaska and Russia. So we have only 6K of Yupik English sentence pairs from the Bible. On the other hand, Inuktitut is an indigenous language spoken in the Nunavut territory, where they have their own legislative assembly conducted in both Inuktitut and English. So we are honored to receive the original handset of the Nunavut Legislative Assembly. After some data cleaning and sentence alignment, we created an Inuktitut English parallel corpora that consists of 1.3 million sentence pairs. So, and Yupik and Inuktitut, they are sister languages in the same language family that hopefully could be translated into each other with acceptable quality without huge amount of data. Maybe through a rule-based approach. So we wish to learn from participating in Kazakh English could be useful or could be useful when we work on Canadian English language translation. So going back to Kazakh English translation problem. So a typical pipeline to tackle this situation is pivoting through the language with higher amount of parallel resources to both the source and target languages. So that is Russian in this case, the pivoting language. Since we have very large amount of Russian English data, so this red path here, we could build a decent NMT system. So we translate Russian the Kazakh source into Russian, and then use the Russian English system to translate it into English. So the problem of this solution is that the system has now never seen the original Kazakh. The information lost or corrupted through this chain is lost permanently. Another solution could be translating the Russian. So we have a lot of Russian English parallel data. We translate all of them into some kind of pseudo Kazakh or synthetic Kazakh for training the Kazakh English system. So the problem of this approach is that now the pseudo Kazakh translated from Russian overwhelm the Kazakh English system. So these are broken Kazakh, like they are not real Kazakh, they are translated from Russian. So they could be in bad quality. And now we have overwhelmingly large amount of bad Kazakh in training this system. So, and also, there's no way for the system to tell apart like which are real good Kazakh and which are bad Kazakh. So although both approach make good use of like the additional Kazakh Russian and Russian English available data, each of them still have their own deficiency. So we said like, why not use both approach? Why not both? So by using a multi-source attention, we can combine the pivoting and the synthetic approaches together and make the most out of all the available data. We use the Russian Kazakh system to translate the Kazakh English and the Russian English parallel data into each other, and then supply both of them to a multi-source system. And then let the neural network to decide which and what to focus on when it finds necessary. So to make it work, so we have to, so we used the Amazon Sockeye NMT toolkit as our base. And to make it work, we have to implement multiple encoders in the Sockeye system, and where each encoder will handle one source. And then we have additional attention layer here that before entering the decoder, so that the network will combine the output of each encoder via our product and sum operation. So so it will become it will merge all these source back into one sequence of vector again for decoding. So our results show that like our multi-source system turned out to be very useful in this situation. So BLUE and EC1 are two different evaluation metric used to do a translation quality by comparing the system translation output against a human reference translation. So blue is the most widely used metric, and EC1 is a new and more accurate metric. Again, I will further talk about these metrics later. At this moment, so let's just trust me that for both metrics, the higher the score means the better the translation quality. So the single source baseline here that use only the 200K parallel Kazakh English data is unsurprisingly giving us the worst score of 9.9 blue and 59 EC1. So if we ignore the fact that Russian is a completely different language from Kazakh, we simply concatenate the 14 million Russian English and the 200K Kazakh English data together to train a single NMT system. The system benefits from seeing a lot more English sentences and able to translate Kazakh a little bit better. Both pivoting and synthetic augmentation approach further improves the translation quality. The synthetic approach, because like it's the more real data, more real data. So above all, our multi-source outperformed the pivoting approach by 4.2 blue and 2.7 EC1. So the benefit of the multi-source is encoding each language separately so that the system won't be confused which language it is looking at. At the same time, it makes the most use out of all the available data. So in terms of MT system building, our team has done a lot more other work too. Provide production level French to and from English MT systems to the Canadian federal government and parliament. We have also worked on adapting MT system to social media domain for public security departments. Recently, we are very active in research on Inuktitut and low resource language MT. This year, we created a new release of the Nunavut Hansat Inuktitut English Parallel Corpus. We organized the and participate in the WMT 20 Inuktitut to and from English news translation task. And also, we also participate in the low resource MT share task. All these work are done on our high performance computing facilities. So I promised you that I will talk more about MT evaluation metrics. So here we are. I'm going to talk about EC, a new and leading translation quality evaluation and estimation metric that we developed at the NRC. So, let me first take a step back and ask you one question. So what makes a translation useful for the user? So everyone has used some kind of translation service before. So what makes a translation useful? So a useful translation is one from which the human readers, like you and me, accurately understand the event structure, who did what to whom, when, where, why, and how from the original input sentence. However, the most widely used MT evaluation metric, which is blue, failed to accurately reflect translation utility or translation quality. So let's look at the following example. So MT1, so far the sale in the mainland of China for nearly 2 months of SK2 line of products. Like it's a bunch of words, but you have no idea what it is trying to say. MT2, so far nearly 2 months SK2 the sale of products in the mainland of China to resume sales. Okay, now you have slightly better idea. SK2 is trying to resume sales. It's better than MT1. And MT3, so far in the mainland of China to stop selling nearly 2 months of SK2 product sales resume. Okay, now you know what is the nearly 2 months it's there doing. So if I ask you, and here is the reference translation and the original source. So if I ask you which one in these three translation is better translation, you will probably say MT1 is the worst, MT2 is better, and MT3 is the best. However, Blue is saying completely reverse result. Why is it so? So Blue is saying MT1 is the best. Why is it so? Because Blue is a n-gram exact matching metric. And it happens that MT1 has a longest exact match of SK-2 with the reference. So this Blue metric is not useful to tell us about like translation quality. And if our system is trying to optimize against Blue, we will have like disastrous result. So we ask this question, why don't we just evaluate translation using the event structure, or what we call the semantic role labeling, or SRL. So we look at the reference translation, and then we can extract the who did what to whom, when, where, why, and how, the event structure from the reference translation, and then compare this structure with the structure in the machine translation. So because MT1 does not have a verb, so the semantic role labeler will be failed to extract the structure. Like there's no event, it's just a sequence of noun phrase, right? So in contrast, MT3, we can have a semantic structure. And if we look at the number of n-gram matches and the number of SRL matches, n-gram matches will say that like MT1 has higher number of matches, but like in SRL, MT3 will have a higher number of SRL matches. So this showed that like semantic role labeling will be more useful for evaluating machine translation. So this is how we design the EC evaluation metric. So we first use semantic parsers to extract the event structure of both the reference and the machine translation. And then we use alignment approach, semantic according to the phrasal similarity to align the semantic roles, and then we compute the EC score. So this is how EC is computed. Of course, I'm not going to torture you to like read all those equations. So there is a graphical explanation. So we have the hypothesis or the machine translation on one side, and then we could have the input or the reference translation on the other side. So first, we extract the tree structure, the semantic tree structure, or the event structure of this sentence. And then at the argument or at the semantic role level, they are actually the phrase that we have, for example, nearly 2 months or for almost 2 months. And then we can encode these phrase, like the tokens in these phrases, into like embeddings. And then we can compute the cosine similarity between these embeddings to get the lexical similarities. And then we can aggregate them together, become the phrasal similarities. So we can have precision and recall depending the denominator is the reference or the machine translation. We can do the same for the complete sentence. And then we can aggregate all the row similarity into a frame similarity. And then we can aggregate the frame similarity into the event structure similarity. And then we can have a semantic precision or semantic recall by combining the semantic structural semantic similarity and the sentence phrasal similarity together. And then that will be a weighted sum of this precision and recall will be our EC score. So you can see that like here, I said that like it could be either the input or the reference translation. If we are using the human reference translation, it will be empty evaluation metric. So we are comparing the machine translation and human reference translation. They are both in the same language. So what we need is a large monolingual corpora for building the contextual embedding so that we can compute the lexical similarities using cosine similarity. And then like we can, through the EC algorithm, we can finally get a EC1 score. Or we can compare the machine translation with the original source input. So then that will be what we call a empty quality estimation metric. That will be a cross-lingual semantic similarity. So we will use cross-lingual embeddings extracted, for example, from Multilingual BERT, or this year we improved EC2 with using XLM Wilberta, and also cross-lingual. We learned to do a cross-lingual linear projection to transform the source embeddings into target language vector space. So using the same algorithm, but changing the monolingual embeddings to cross-lingual embeddings, we can have cross-lingual semantic similarity score. So this is, EC has continuously entered these WMT metric share task, and it is shown in consecutive years that it is the leading metric in the research field. So, this metric share task usually has like 12 to like 20 translation direction being evaluated, and you can see that EC1, like the bold phase number means statistically that metric rank first among all metrics. So this is the 2019 result, and with the new improvement for we do this year, we can see that the correlation with human is even higher this year. So the interesting thing about EC2 is that like EC2 is more than an empty quality estimation metric. We can use it for cross-lingual semantic textual similarity. So it is a task like randomly we pick sentences from two languages, and then we can tell you whether these two sentences are unrelated or they are identical in meaning. Or we can use EC2 for parallel corpus filtering. So the web can be used as a multilingual data source. We can crawl the web, we can scrape it, but like after scraping it, it will be a very dirty, very noisy parallel corpora. So EC2 can be used for like scoring the usefulness of this sentence pair for training MT. So we re-rank the dirty corpus, and then we can like extract the best data out of this re-ranked dirty corpus. So there are a lot of other work we do using high performance computing. On language learning, we have we work on hypernym discovery, which is a task of discovering word pairs with its relations. So, for example, monkey is an animal. So I identify. So animal will be a hypernym of monkey. So we try to like we give you a whole collection of words, and then you try to discover this kind of relation from that collection. Textile transfer is like text generation with altered sentiment, tense, mood, or politeness. So if we give you a sentence and then we say like, can you make it more polite for me? Then it will output our sentence in the same meaning, but like the style of the writing will be more polite. Language identification is recognizing the language used in short text, and social media text mining, we have worked on it as well. In particular, we are interested in change point detection. So social media is a text stream. We try to identify, detect the change point in this text stream. So to conclude my presentation, we have a few ideas for potential collaboration on Fugaku. So I know that like the natural language understanding team in RIKEN particularly interested in evaluating short answers. So EC could be useful in like evaluating the meaning similarity between short answers, dialogues, or summaries. We are also interested in improving the massively multilingual pre-trained language model. For example, expanding the set of supported language without training from scratch. So currently, Multilingual BERT or XLM Roberta support 100 languages. But like if we want to use this kind of model for example, evaluating Inuktitut, it's not possible because it is not supported in these languages. So we want to take advantages of these model, but like without training the whole model from scratch. Also, learning to better capture semantic representations across languages. So the post hoc cross-lingual linear projection is able to improve EC performance. That indicates that like in these massively multilingual model, inside it, actually each language has its cluster in its own subspace. Like they're not really representing the meaning representation. So So we want to like better fuse the individual monolingual subspace better, so that it is actually a meaning concept representation, rather than like each language has its own cluster. Also, when we work on indigenous languages, right now we are at the stage that we want to produce more text-to-speech system to encourage the community to retain their languages. So we want to work on unsupervised contextual speech embeddings, which is something like a BERT for speech, to help building these text-to-speech system. So this is the end of my presentation, and thank you very much.
All right, thank you very much, Jackie. So we have 3 questions from the audience on Zoom chat. So let me pick up the first one. So what is the reference score for human translation for each metric? I guess it's in around mentioning about slide, maybe around 9 to 10.
I am having problems seeing the chat. Could you repeat the question again?
Oh, what?
Okay.
What?
I see it now.
Okay.
If I understand, what is the reference score for human translation for each metric? So if you are comparing the exact same translation to each other, then that will be 100. But like if it is different translation from 2 different translator, it depends. It depends on like how different they are when they are writing their translation. It could be for Blue, it could be range from like 100 to like maybe just like they can share, like you can express the same thing without sharing any word, right? So that could be 0. So that's why, like if we use Blue, that would be a problem. Does that answer your question?
Okay, thank you. So let me pick up one question from different audience. So from Benjamin. So he said, if I understand correctly, the VAC metric requires semantic load leveler in the target languages. How does the quality of the semantic load leveler impact the evaluation? And did you try different semantic representations?
So the second part of the question, I have not tried FrameNet or AMR. The interesting about the quality of the semantic role labeler is that like it does not really matter, because like what actually matters is like the machine translation is usually bad anyway. If the semantic role labeler is able to pick up some structure, then that will be useful. The accuracy of the semantic role labeler actually, first of all, they're not. So what I have tried using Assert, Sana, and Mate. So their difference is not that much in terms of like the final easy score correlation with human. Yeah.
All right, thank you very much. So we are running out of time, so it might be good to continue this discussion on Slack channel, if you do not mind. And one comment, and so regarding the collaborations from Satoshi, so for running BERT and other transformer based on natural machine translation framework on Fugaku. Please contact Alex. He is he's also doing natural language processing. He's in high performance AI team, and his address is written in this chat. And also, as Satoshi Matsuo touched on, in his talk in yesterday's talk, we have a deep learning tuning and porting project called DL for Fugaku project, and the BERT is listed as one of priority neural network. It will be we haven't worked on yet, but it will be supported at some time. That's a future point.
Yeah.